My name is Malar Chakravarty. So for those of you who've never come to this seminar series before, this is the first of the academic year spanning 2020, 2021. We typically go every Wednesday, roughly, between now and about May-ish or so, depending on who we have. And as you've noticed, since we've hit the pandemic, we've taken this completely online. And so thank you all for making time to come. This particular lecture, as I mentioned before, is being recorded and will probably become a YouTube post at some point. So just keep that in mind if you don't want your face to be seen on camera. In addition, if you have questions you'd like to ask during the seminar series, during this talk, sorry, please, you can either put up your hand. If you don't know how to do that, you can just say something in the chat, and I'll do my best to interrupt an opportune time to either let you in to talk, to give the question, or I'll pose it myself, stating your name if I can. With that, we're gonna get started. We've changed how we select speakers this year. And so we formed a really great committee who I probably should have taken the time to create slides about and introduce properly today, and I didn't. So I will do that in a subsequent lecture, just so you know who's selecting our speakers and who you can get in touch with if you have speaker selection suggestions. So with that said, I'm gonna introduce our very first speaker, who's consistently our first speaker for the seminar series, I think 5 or 6 years running, or pretty close. And it's Jamie Neer, who is an assistant professor in the Department of Psychiatry, someone we all know and love. And he's kind enough to give us this intro on kind of the basics of MR and MR imaging that he'll be giving today. So without further ado, Jamie, I'll let you take over the talk. Thanks a lot for, once again, volunteering to do this.
So yeah, thanks for inviting me. I'm really happy to be here to kick off this next academic year's session of the CIC lecture series. I don't think it gets said enough, but this series is really, I think, a special thing for the CIC and for the Douglas. We get a lot of really great speakers, not just talking about myself, but there's lots of others too. So thank you, Malar, for organizing it. He's been organizing it ever since he got to the Douglas back in, I think, 2014. So really, thanks a lot, Malar, for all the organization.
Thanks, Jimmy.
So here comes the introduction to MRI. So today I'm going to try and cover, a lot of the basics. And so first we'll talk about what is spin, what are magnetic moments, and what is magnetization. Then we'll talk about excitation. So how do you excite the magnetization? And then we'll go into how to make images. So how do we get this spatial information that ends up becoming our image? And to do that, we'll talk a little bit about something called K-space, which many people have heard about, some people are afraid of. I think it's, hopefully I'll try and give you an intuitive feel for what K-space is and how to understand K-space. Then we'll just talk about a few different ways of filling K-space, or ways of acquiring images, really. So gradient echo images, EPI, and spin echo. And lastly, I'll just talk a little bit about relaxation. And the last few topics are really just glossing over because we don't have too much time. So again, as Malar said, if you want to interrupt at any point and ask a question, please let me know. Malar is going to interrupt me because I'm not watching the chat or the hands going up. But yeah, do please speak up if there's something that's not clear. So the first question is, what makes MRI special? So first of all, it's an imaging technique that is safe and non-invasive. So unlike a lot of other techniques that might involve ionizing radiation, MRI is very safe. I think it's also important that the way that MRI images are generated is totally unique compared to a lot of other techniques. And this, I think, leads to some of the versatility of MR. It gives us a way of measuring lots of different properties of the tissue, including things like relaxation, diffusion of water molecules within the tissue, magnetic susceptibility, temperature, pH, elasticity, things like neural activity using bold fMRI, concentrations of metabolites in the tissue using MR spectroscopy, which is something I do a lot of, and the list goes on. So this is why MR imaging is such a powerful tool that everybody in the research world and also in clinic is really excited about. So how does it work, and what is magnetic resonance? This is a new slide that I haven't used before, but I'm going to try and frame magnetic resonance as a bunch of protons singing in unison. And what we're trying to get the protons to sing, and these are little singers here. You can see their faces singing, their protons. And we're trying to detect that signal. But we also have a lot of control over the signal. We can make them sing. We can tell them when to sing. We can control the frequency of their singing. And all of that, how do we control that? Well, we do that with magnetic fields. So we introduce a strong magnetic field, and this kind of causes all of the spins to line up together in ready formation. And then we apply some radio frequency energy, and the radio frequency energy kind of excites them and causes them to emit their voices, their electromagnetic signals, which are their little song. And so we listen to that, and that's how we make that's magnetic resonance, and that's what we use to detect these protons. So what happens when I take well, first of all, what is a spin? So when I talk about spins through this talk, I'm going to be talking about protons. So a proton, or 1H nucleus, it has a positive charge and it's spinning. And if you take a charge and you move it around, this generates a magnetic field. And a spinning charge generates a magnetic dipole moment, which we can call mu. And this points along the axis of the spin. So if that's a spinning basketball, if I'm spinning a basketball on my finger, the magnetic moment of that spinning charged basketball is pointing in the direction of my finger. Okay? If I have an ensemble of spinning protons, they all have their own magnetic moments, they're all spinning. But under normal conditions, all of those magnetic moments are pointing in different directions. And so the net magnetic moment is 0. They all cancel each other out, and roughly there's nothing to detect. So that's no good. We want to detect these magnetic moments. So how do we do that? Well, we can expose them to a strong magnetic field. And what that does is it causes two things to happen. First, spins, when they're exposed to a magnetic field, these spins are either going to align with the magnetic field or against it, kind of like you see in this picture here. So you have some pointing up and some pointing down. And these are related to the energy of the proton. So these are the two allowed quantum energy states of the system. And then once they're kind of pointing roughly aligned with that B0 field, they're going to precess about it. So they're going to start rotating about that magnetic field like a spinning top. And the frequency of precession, which we call the Larmor frequency, is given by some constant called gamma, which is the gyromagnetic ratio, multiplied by the strength of the B0 field. So in other words, the stronger the magnetic field that they experience, the faster they're going to precess, and the higher the frequency of oscillation is going to be. So if we have an ensemble of those spinning protons, some are going to align up, spin up, and some are going to align down in the spin down state. And we can kind of think of them using a model that looks like two cones. So the ones on the top cone are pointing up, and they're all spinning about the B0 field, but they have a different phase. So they're kind of distributed around this cone. And in the spin down state, same thing. They're all pointing down, and they're precessing, but their phases are distributed around that cone. It just happens that this upper spin state is slightly preferable in terms of energy. And so you get more spins lining up in the top state compared to in the bottom state. And as a result, there's a net magnetization, or a net magnetic moment, which we call the magnetization. And this ends up being parallel to B0. So this is our M0. This is the sum of all of the little magnetic moments. We call it our magnetization. And it's in equilibrium, it's parallel to B0, parallel to the applied magnetic field.
Jamie,
Yes.
there's a little question in the chat, which is a good one. Why are they spinning at an angle?
This is a good question. So I don't have a great answer, other than the allowed quantum energy state for them is not to be perfectly aligned with the field, but to be offset and to be and to process about that field. That's a really bad answer. I don't know. I actually don't know the answer to why they don't just line straight up with the field. But you'd have to talk to probably a hardcore quantum physicist to tell you the answer to that.
But if they did line up directly with the field, they actually would never process too, right?
They wouldn't process, but we could still probably tip them away. Well, that's a good question.
So you would actually never get this kind of precession frequency that you can manipulate as a result.
Yeah, that's probably true. Yeah. So yeah, it's interesting to think about. I think that, there are different types of spins. We have spin 1/2 spins, which have this property. There's also spin 3/2 and other kind of spins. And the picture gets more complicated when you start talking about different spin quantum numbers. You get more than two states. You might have 3 or 5 states. And in that case, you'll get different angles of kind of orientation. And so that might sort of be closer to the situation where if you had some aligned with the actual Z or with the B0 axis. Anyway, sorry that's not a perfect answer, but just trust me, this is what it looks like with protons. Sorry?
I was wondering if Gina is satisfied with the answer. Does she have any follow-up? Thank you. I got a good thank you. There you go.
Okay. Anyway, so this is what it looks like when this ensemble of protons is now exposed to a magnetic field and it's in equilibrium. We get a magnetization that's parallel to B0. All of the X and Y components are canceling out still because of the sort of equal phase distribution around those cones. So we don't have any X and Y component yet. But what we really want to do is detect this magnetization. And when it's in its equilibrium state, it's very small and very hard to detect because it's not moving. So in order to detect it, we need to disturb it. So we've set it up. We need to disturb the system. We need to disturb this magnetization away from its equilibrium position in order to detect it. And so in order to do that, we can use a second magnetic field, which is a rotating magnetic field in the transverse plane, the XY plane. And this type of magnetization can tip our magnetization, or sorry, this type of magnetic field can tip our magnetization away from the longitudinal axis. So here's a little video of how that works. This is our magnetization. And when I hit play, you're going to see a little B1 vector that appears. That's another oscillating magnetic field. And what it tends to do is it tips our magnetization away from the z-axis into the transverse plane, the xy plane. And as it oscillates, it's going to emit a radio frequency signal that we can detect. And this is the NMR signal that I was talking about earlier, the singing of the protons. All singing together makes this magnetization that we can detect. So that's excitation. But what we're looking at here is a little complicated because it's in the lab frame. There's a lot of spinning going on. Generally, when we talk about excitation, we can visualize it in what's called a rotating frame. And so to do this, we think of a frame of reference that's rotating at the same frequency as the Larmor frequency. And if we were to visualize the same system in that frame of reference, you'd get something like this. So you have your magnetization. Now I'm calling the axes X prime, Y prime, and Z prime to indicate that this is a rotating frame of reference. And if I click play, now my B1 vector, which is my excitation field, is stationary, and my magnetization just tips nicely down. It's rotating about the B1 vector. And this is what magnetization vectors do in magnetic moments. When they're exposed to a magnetic field, they rotate about it. And so what's really happening here is the magnetization is rotating about the applied B1 field. And that's how you do excitation. And now we can detect this magnetization because it's in the transverse plane. So what have we described so far? We know that you take your spins, you put them in a magnetic field, you apply some RF energy inside the system, and then you record the emitted radio frequency signal at the end. So the signal that's given off by the spinning magnetization, we detect that. And I didn't mention how we detect it, but we use a radio frequency coil, like a little antenna that can detect the signal that comes from that. One thing I also maybe didn't mention is that both the emitted signal from the, the magnetization and the excitation RF have to be at this same frequency, and that frequency is the Larmor frequency. So it's the same gamma times B0. Cool. So the next question is, how do we make images from this phenomenon? And this was the topic of the research of Paul Lauterbur and Peter Mansfield, who back in 1973 both independently sort of devised a way to make images from the NMR, magnetic resonance signals. And this development got them the Nobel Prize. And so the idea here is to use a magnetic field gradient to spatially encode the MRI signal. So here's a couple of sort of thought experiments to help understand what a gradient is and what it does. So, sorry, my screen is a little blocked. Okay, so first of all, imagine you had just a vial of pure water, and you put it into a magnetic field, and then you excite the sample using an RF pulse, and you record the emitted signal. What is that NMR signal going to look like? Well, since all of the protons experience the same B0 field, they are all going to resonate at the exact same frequency. And so the resulting signal will just be an oscillating signal with one particular frequency. And regardless of what the shape of your sample is, the shape of your vial, the result is going to be approximately the same. You're just going to have one frequency because the magnetic field is constant everywhere. And if I take the Fourier transform of this signal, I'm going to get a peak in the frequency domain that just looks like a single frequency. Okay, so this is my time domain signal, the signal that is actually emitted by the magnetization. And this is my Fourier transform, which is a measure of the frequency content of that signal. So now let's repeat that experiment, but with a gradient. So first of all, let's imagine we have two vials instead of one, and they're at different positions along the x-axis. And now I'm going to apply a magnetic field along the x-axis so that at different positions, x, you're going to have different magnetic field strengths. So what will that signal look like? So here are my two vials. Call them x1 and y1, or sorry, they're at positions x1 and x2. And also we've applied a magnetic field gradient, so we'll call this gradient G, and this represents the magnetic field at each position. So at position 1, the magnetic field is low, and at position x2, the magnetic field is a little bit higher, okay? And the magnetization in each vial is given by the letter M. So what happens if I collect the MR signal from these two vials? Well, I'm going to have two signals, one from each vial. This blue signal is from the large vial, and it has a taller amplitude because the vial is bigger, but the frequency is slower because it's in a lower magnetic field. Likewise, from the other vial, a small vial, we have a lower starting amplitude because the vial is a bit smaller, but the frequency is higher. You get more faster oscillation because it's in a higher magnetic field. Okay? Now, the signal that I'm going to detect in this system is the sum of those two. So if I just add these two together, I'm going to get this signal that looks like this. And I can write the equation of that signal pretty easily just by summing the individual equations of those two signals. And if this math doesn't look nice to you, basically these are just equations of the two different oscillating sort of decaying sinusoids here. And here I've just written the sum of those two, okay? And what I'm going to do now is I'm going to take the Fourier transform of that to look at the frequency content. And so if I, not a minute, I lost my mouse. Oh, there it is. So I took the Fourier transform and I get these two peaks. And you can notice right away that this already looks like a one-dimensional projection of our vials. So this peak here is right at the position of vial 1, and this smaller peak is at the position of vial 2, and the heights of the peaks actually represent the size of each vial. And so on the frequency axis, I actually have a measure of the frequency of their signals, but I can convert that to position because I know the relationship between position and frequency based on the gradient strength that I used. So here it gives me a way of generating basically a 1D image of my system there. And so this is called, this is basically the technique that was used in early MRI to generate the first images. So they would do projections of the sample along different angles, and then they can use a technique called projection reconstruction to reconstruct the full two-dimensional structure of the sample. This is the one used by Paul Lauterbur in 1973. So let's going just back to that example. If I have 2 vials in my sample, then I'm going to have 2 frequency components in my signal. But what happens if and here are my 2 frequency components, right? Okay, we're going to do a little math manipulation now to introduce what K-space is. So in this equation, you have gamma times the gradient strength times time, okay? If I replace gamma times gradient times time with just the letter K, or a function K of t, then my equation looks a little different. And here it is. So K of t is just if the gradients are static, it's just gamma times time. But you can actually fully generalize this for the case of an oscillating gradient or time varying gradient. If you say that K is equal to the integral of the gradient in time. So this is basically saying that K is just the cumulative area under the gradient as a function of time. And so with that small manipulation, we've just replaced some of these terms with the letter K. Now we can imagine here that, let's say our sample, instead of having 2 vials, let's say we have a continuous sample that looks like a person. Now what's the signal going to look like now? Well, what we can do is imagine our sample as an infinite number of vials, and then we can sum the signal from all of those vials together to get what our final signal is going to look like. And to sum an infinite number of small vials, we just use an integral over all space. So we're integrating all over space. The signal from a lot of small sort of sections of tissue along the x direction, and each one of those is going to give a frequency or it's going to give a signal at the frequency corresponding to the gradient that's experienced at that point. And the signal that I get is just going to be the sum of all of those signals from those tiny little vials or imaginary vials. So we can expand this in 2 dimensions. And so not just in the x direction, but we can do this in both the x and y directions. And what we see is that our signal is now, it's a function of the magnetization density of the sample at all spatial positions and multiplied by this exponential that is a function of K. But the thing that we actually want is, so this is what we've measured, but the thing that we're actually after is this value mxy, which is the magnetization density of our sample. And if you look at this equation, and some smarter mathematicians than me looked at it and said, well, this is just a Fourier transform. And so they realized that if you take the Fourier transform of the signal, you can actually then get back your mxy, which is the thing that we want. This is the image of our sample. So all we really have to do then is to acquire our image, our signals in K-space, and we have to fully sample our image in K-space and take the Fourier transform of that K-space signal to give us an image of the sample. And K-space, well, how do we sample in K-space? Well, we use the gradients to sample different points in K-space. And since we know that K is the area under the gradient, then we can sample our image at using different gradient strengths and different timings to fully sample this K-space here. And so one thing to note is that all of our signals are discrete. We use digital sampling to sample all of our signals. And in order to, that means our K-space is going to be digital and or it's going to be discrete, and our image is also discrete with pixels. And so we have to follow some rules in order to make sure that K-space is properly sampled. And so if I show here, this is K-space on the left, this is image space on the right, and they're related to each other by this Fourier transform. I can say that the distance between samples in K-space is called delta K. The distance between pixels in image space is delta X. This is our spatial resolution. The field of view in K-space is FOV-K, and the field of view in image space is FOV-X. And the rules of sampling, or the sort of the sampling, I guess, criteria that we have to follow are that for an image with an FOV given by this, our spacing, we need to choose the delta K such that the field of view is equal to 1 over delta K. Likewise, for a given spatial resolution, we need to sample in K-space with a field of view of 1 over, I guess it's, the reciprocal of our spatial resolution. And so by following those rules, we can make sure that we get an image that has the field of view and the spatial resolution that we want. Okay. So, what I've,
quick question.
there's another question? Yeah.
Again from Gino, which is an interesting one. Since protons are everywhere, why are we only detecting biological tissues upon magnetization? Which I think we'll get to shortly, I believe, right?
Since protons are everywhere, why are we only detecting biological tissue?
Upon magnetization.
So
basically, they're like protons are everywhere in the environment. And why are we only detecting the stuff that's in our case, the brain, for example?
I see. So we're going to detect water protons that are everywhere. Protons in other environments might be more difficult to detect because often, they're in lower concentration, or they might not give off a lot of signal because of their relaxation properties or something. But usually we detect what we want to based on where we put the RF coil. So we have this detector, which is the RF coil, and we usually put it close to the sample where we want to be observing. So if I want to detect the brain, my RF coil goes right over the brain, and I'm going to detect the signals that come from inside that area. And we usually try and limit the number of other things that are nearby that we could be detecting. So hopefully does that answer the question?
While Gina's telling us if it answers the question or not, is it worth saying that everything's kind of tuned towards detecting the protons in hydrogen and water for, let's say structural images, for example, right?
Oh, yeah.
We have that type of optimization that we've done over the course of time as well, right?
Yes, yeah. And I guess the other thing to note is I'm specifically talking about water protons here. So if you're talking about protons in other nuclei, we can't really, so like, let's say I'm like helium or something, there's 2 protons there, but by virtue of being, in an atom with another, or in a, together with another proton in a helium atom, it no longer has the same NMR properties of a hydrogen proton. So this is really only hydrogen protons, if that answers that part of your question. And Millar is right. We try and tailor it to looking at water only, or specifically water. And then we use the coil to specifically localize where we're looking at signal. So within the tissue, that like the brain or something, so that we're not looking at signal from the leg or the knee if we want to look at the brain. Okay, so if that's okay, I'll continue.
Yep, thanks.
Okay, so in the next section, I'm going to talk a little bit about how we sample K-space. So how do we make sure that we cover all of K-space, and how do we make sure that we sample it in a time-efficient way? And so that's how this next section is going to cover. So before we talk about that, just for a quick, it also helps to talk about this as sort of forming a 2D image. In order to form a 2D image, we want to first excite only a slice of tissue. And this might also help answer your question. So there's protons throughout the whole brain, but if I just want to look at a single slice of the image, I might do something called slice selection before I start filling K-space, and that means that I'm only going to be looking at protons or signals that are inside a specific slice of tissue. Okay, and so how does that work? Well, we do something called slice selective excitation, and that involves applying a radio frequency pulse that has a frequency selective excitation band. So here's an example of an RF pulse. This is an excitation pulse that has a roughly sync-shaped envelope, and this is what the pulse looks like in the time domain. This is if I look at the Fourier transform of this pulse, I can see what frequency content is excited by this pulse, and you can see it's roughly square-shaped. So that means that this pulse is going to produce a 90-degree excitation only for spins that have Larmor frequencies within this range of frequencies here. Okay, and if I combine a pulse like this, a frequency selective RF pulse, with a gradient, a magnetic field gradient, then I can actually do a slice selection. And so here's a graph of frequency versus position. And I've got a line here indicating that my gradient is on. So I've set up a gradient so that spins have different Larmor frequencies as a function of position. And if I apply this frequency selective RF pulse, here you can see I'm only going to select spins that are inside this position area here. And I can change the strength of my gradient to actually change the thickness of my slice as well. So this gives us control of how big the slice is that we're going to select, and we can also position it where we want to. And so once we've excited a slice, now we're looking only at spins that are inside a particular slice of tissue, and we can go ahead and start doing some spatial encoding or sampling of K-space in order to reconstruct an image of that slice. You can see here that stronger gradients up here result in thinner slices, and weaker gradients result in thicker slices. So we've excited our slice now. We want to go ahead and do some spatial encoding within that slice. And this is also called sampling K-space or filling K-space. And we just remember that the definition of K is that it basically says that at any particular time, the position that we're at in K-space is given by the time integral of the gradients applied up to that point. And so this is basically the equivalent of taking the area under the gradient. Okay, so here's a pulse sequence. This is called a gradient echo sequence, and it starts with an RF pulse to excite the magnetization. This would be a slice selective RF pulse. My slice select gradient is on the z-axis, so I'm exciting a slice that's sort of perpendicular to the z-axis. And then I'm going to do some phase encoding and some reading out. So, and this is my K-space, okay? So let's look at what happens on the y-axis. My gradient starts at 0, and then I have a negative gradient, which goes for some time, and then it turns off again. So during that negative gradient, I'm going to be moving to the left side of K-space because it's going to be going, this is the origin, this is 0 here. So I'm going to be moving to, sorry, ky is this way, so I'm going to be going negative in ky. I've also got a negative gradient in the x direction, so I'm going to be moving negative in the x direction. Oops, where I started it. So here you can see what's happening. Maybe I'll explain it as it goes. So during this lobe, this is kind of like our rewinder section where we're going from the center of K-space off to one of the edges of K-space. And then at the end, we turn off the y gradient and we only turn on the x gradient. And during that x gradient, we're going to be moving across K-space in the x direction, okay? And so in this gradient echo sequence, we can sample different lines of K-space to fill, to actually fill K-space the way we want. And so this is sometimes called a flash sequence. And each line through K-space here is called an echo. The x gradient here is called our frequency encoding gradient, and the y gradient, which is this one here, is our phase encoding gradient. And so we really only apply the phase encoding gradient before we start acquiring signal. And this is our ADC. So the ADC is on during these horizontal lines in K-space. So we're collecting signal along these lines.
Jamie?
Yes.
We have a question from Daniel. I'm assuming you need to send, I think this is answered now, but I'm assuming you need to send 2 RF pulses in both axes to get a 2D image. Is that correct? Do you feel like that's answered, Daniel, properly for you?
I can answer it anyway. To get a 2D image, you only need 1 RF pulse. You just need this one to select the slice. So now once you've selected the slice, you can do the rest of the encoding with just gradients. Okay, so you excite the entire slice, and then the magnetization within that slice is encoded just using gradients. So basically these gradients here, which move us around K-space. So that gives us a 2D image. I hope that's clear.
Yeah.
Okay. So then we're going to fill K-space line by line, and we're just repeating this over and over with different phase encode gradients to get the different vertical, or the different KY lines. And then once we've filled K-space, we take the 2D Fourier transform to get the image. If you want good resolution, you have to repeat this many times with different phase encoding gradients. And so let's say I wanted a 256 by 256 matrix size. I'd have to repeat this 256 times with 256 different GY values. And this is going to take me about 26 seconds to do it if I repeated it every 100 milliseconds. So you can see for a single slice, it could take a while to do, to image this way. We also have something called an echo time, which is the time between the beginning of the middle of the excitation pulse and the center of the echo, which is sort of where the center of K-space is. And finally, the repetition time is the time between these excitations, okay? Between the repeated excitations. So that, as you saw before, if you want high resolution with that previous gradient echo sequence, it takes quite a few excitations. But here's a way of getting sampling K-space more quickly. Okay, so the way this works is you have a single excitation, which is also slice selective on with a Z gradient, and then you have a rewind in X and Y. So this is going to take us to the negative in both X and Y. So it's going to take us to the bottom left corner of K-space. And then the gradient starts zigzagging back and forth in the X direction. So that means it's going to be going back and forth like this. And in between each zigzag, there's a little Y blip in the upward direction. So we're going to be moving up in between each K-space line. And so the result is kind of like this sneaking pattern, which you'll see here. So we rewind to the corner of K-space, and then we just start sneaking up through K-space using this trajectory, which is called an EPI, or an echo-planar imaging trajectory. And in this way, we can actually sample the whole slab of K-space, the whole slice of K-space, in just one single excitation. So with 1 RF pulse, we can sample the whole thing, and that can be done in around 100 milliseconds or so. We can get an entire image of K-space, or an entire slice. And so this EPI technique is probably the most common one for functional MRI, which is how we get really high temporal resolution to measure brain activity. And the one issue with this is because it has a very long readout duration, it can be susceptible to some artifacts due to magnetic field inhomogeneity. So there are many other, I've shown you 2. I've shown you a gradient echo type trajectory and an EPI. And there are many others. So we also have spiral trajectories where the K-space pattern looks like a spiral to cover the whole thing quickly. There are radial trajectories where you have lines going from the center of K-space to the edges, almost like a pinwheel. Propeller, which is similar, but instead of single lines, you have slabs of lines that are rotated. And segmented EPI, where you do the same as what I just showed in EPI, but you don't, instead of sampling the entire K-space all at once, you could sample sections of it and then stitch them together at the end from different TRs. So some of these trajectories give us sampling that is Cartesian. In other words, our samples follow a Cartesian grid along an XY grid. And if in this case, we can reconstruct our image by just doing a standard two-dimensional Fourier transform, or FFT. But some of the trajectories are non-Cartesian, like a spiral. So the samples in a spiral are not going to fall along a perfect Cartesian grid in the XY. And so in this case, we can't just use a simple FFT. We might need some kind of alternatives. And so there's some other sequences we haven't talked about. There are spin echo, turbo spin echo, fast spin echo, rare, gradient and spin echo, and steady state free precession type sequences. These are all kind of beyond the scope of this lecture, but it gives you an idea of sort of the many, many different ways of sampling case. Some have their kind of advantages and disadvantages, and some have sort of niches where they're really most applicable. So next I'm going to talk a little bit about relaxation. Is everybody okay with the case-based sampling? Did those videos give you an idea how case-based gets sampled? Okay, no more questions. Okay, so going on to relaxation. So after we've excited the magnetization into the transverse plane, it's going to gradually relax back to its equilibrium state along MZ. And this occurs in two ways. One is called T2 relaxation, which is the decay of the transverse component. So when the transverse component of the magnetization kind of dies away. And the other is called T1 relaxation, which is the regrowth of the longitudinal component. So I'm just going to talk about both of these. So T2 and also T2 star are two types of relaxation caused by dephasing of the spins in the transverse plane. Okay. I think I have a video to show you what this looks like. So after you excite the magnetization, all of the spins are pointing along, they're sort of along the, together in the transverse plane. And this produces a large MXY transverse component that we can measure. But with time, the different spins start processing at slightly different rates, and they start to dephase from one another. So I'm going to show you what that looks like in this little video here. So here's our magnetization. It gets excited, and the little gray spins there, they represent individual magnetic moments or individual spins. And you can see that because they're not all perfectly in phase over time, the net magnetization, the big blue vector, starts to shrink over time. And that's this is the thing that we call T2 relaxation. And so we have to try and acquire our signal before too much of the T2 relaxation has occurred. Otherwise, there won't be much signal left to detect. Okay? And this is just a plot of the transverse magnetization as a function of time following this T2 relaxation curve. And it's an exponential decay.
So, Jamie, we have a question. It's going back to the EPI slide.
Yes?
So when you acquire an EPI, it seems like the amplitude of the signal decreases over time. And so the samples in the upper part of K-space might be of lower amplitude. How would you compensate for this issue? Since we need to have symmetric K-space to have real images?
Good question. Yes, so because of T2 relaxation, the lines that are acquired first are going to have a higher intensity than the lines that are acquired near the end of the echo. And this causes, this causes your K-space to not be symmetric. In the end, that asymmetry doesn't ruin the quality of your image completely, but it does cause blurring. So you're basically going to have, you're going to have almost like a weighting function that weights your K-space, and it's the Fourier transform of that weighting function ends up being the blurring function that is convolved with your image. And so it probably looks something like a Gaussian blurring on the resulting image, and so you get a bit of a blurring effect. So I said it doesn't ruin the image, but it does have some detrimental effects, and you obviously need to make sure that you get your EPI quick enough so that by the time you get to the bottom of your K-space, you've got still some signal left. It's not all gone. Does that answer the question?
Well, we're determining that. The other question we have is, I think related to the last slide that you were on. Would the rate of relaxation be a measure of the number of protons in that area, or is the rate independent of the concentration of protons?
I would say the rate is pretty well independent of the number of protons. It has more to do with the properties of the tissue. So sort of almost like a little intuitive rule of thumb for T2 relaxation is that liquids have long T2s. So substances that are like freely moving molecules and spins, they tend to have long T2 relaxation. So they'll decay slowly. And if you have solids or hard tissues that are not free, like where the protons are very immobile, they have very rapid T2 decay. So it's more about the properties of the tissue rather than the concentration of the tissue itself, or the concentration of protons in the tissue, and how freely moving the spins are, or how freely tumbling they are. Okay, so let's continue. I feel like I've got a few minutes left to cover the last few slides. So this is just a bit more on T2 and T2 star relaxation, so and the difference between the two. So after an excitation, the signal decays with this constant T2 star, and T2 star is composed of two components. You can see the relationship here between T2 star and T2, and a third component called T2 prime. So 1 over T2 star equals 1 over T2 plus 1 over T2 prime. T2 is the dephasing that's caused by microscopic magnetic interactions between neighboring spins. So like kind of like if you have a couple of spins that are moving beside each other, they're throwing off little magnetic fields that are changing over time because of their motion, and the experience of those changing magnetic fields causes them to dephase from each other. They're experiencing little changes in the magnetic field, and that causes their alarmer frequencies to shift over time, and they just lose coherence over time. That's T2. T2 prime, which is this one here, is inhomogeneity, or sorry, it's dephasing caused by local sort of macroscopic inhomogeneity in the magnetic field. So the fact that I cannot produce a perfectly uniform magnetic field just because of imperfections in my magnet design, this leads to inhomogeneous magnetic field, which causes its own kind of dephasing, which is this T2 prime component. This part can be reversed, and that's because typically the magnetic field inhomogeneities are time invariant, so we can use that property to actually undo that type of dephasing. But because T2 dephasing is kind of random and it's time varying, we can't get rid of T2 relaxation. So T2 prime, or sorry, T2 star is just the sum of these two. One part which is irreversible, and the other part which is somewhat reversible. So I'm going to pause this. Oh, I can't pause it. Anyway, so what I wanted to talk about next was spin echoes. And unfortunately, I wanted to make my own video that was kind of like the previous videos, but I didn't manage to do that in time. So I found a video online to show what a spin echo is like. And it's just playing over and over again. But really, a spin echo is a type of sequence that has a 90-degree excitation pulse, followed by some delay, and then followed by a 180-degree pulse, which rotates the magnetization by 180 degrees. And then following that time, you get an echo at the end. And this video kind of shows how that works. So you start with your magnetization on Z, it tips into the transverse plane, and you start to get some T2 sort of dephasing. And then after that dephasing happens, you do this 180-degree pulse, which flips the magnetization into another 180 degrees, and they all come back and refocus each other at the end because, well, the phase that happened during this first delay period actually naturally refocuses after the spins have been flipped by 180 degrees in the second, so in the second period here. And so this is called an echo, and the signal at this echo is really independent of T2 prime. So the signal intensity here is going to be, this is sort of how we get rid of the effects of the decay from T2 prime or from magnetic field inhomogeneities, and this means our echo here is purely dependent on T2, and it's not T2 star or T2 prime. So lastly, I'll talk a little bit about T1 relaxation. So T1 relaxation, as I said before, it's the regrowth of the longitudinal magnetization back to its equilibrium position. And so if I have my magnetization, and now I'm showing MZ here, this is the Z magnetization. So if it starts along MZ equals 1, I'm going to apply a 90-degree pulse, which completely destroys my Z magnetization. Right now, my magnetization will be purely in the XY plane. But over time, the Z component is going to regrow until eventually it's completely back to equilibrium. So this is its equilibrium value here. And this decay happens with a time constant of T1. So that's this exponential regrowth of magnetization back to equilibrium. And the time between these excitations is called the repetition time. So you can see here that if I have a long repetition time, I'm going to give my signal enough time to regrow back to its original value. But that means my sequence is going to take a really long time. So what I can do is I can change my TR. I can have a shorter TR and do my excitations more quickly. The issue here is that in that time, I'm not going to give my magnetization enough time to fully regrow back to its equilibrium value. And this is going to cause a little bit of signal decay or signal loss compared to this case. So in this case here, I can acquire my image faster, but I'm going to have lower SNR because I'm going to have less signal recovery during each TR. So this would be a long TR scan, and this would be a short TR scan. Now, you've probably heard of T1 and T2 weighted imaging. And so what that means is that the signal intensity in my image is going to be dependent on either the T1 or the T2 of my tissue. And I can make my images T1 or T2 weighted by adjusting the TR and the TE of my acquisition. So for an acquisition with a short TE and a short TR, my image is going to be T1 weighted. If I have a short TE and a long TR, it's going to be neither T1 or T2 weighted. It's going to be proton density weighted. If I have a long TE and a short TR, it's going to be weighted by both T1 and T2. And if I have a long TE and a long TR, then it's going to be T2 weighted. And so, some particular clinical applications might require T1 weighting, others might require T2 weighting, and we can choose that just by tailoring the echo or the echo time and the repetition time of our imaging experiment. So that's most of what I wanted to cover today. I want to summarize by saying that MRI is an exciting and versatile imaging technology. It's not like any of the other imaging technologies that are out there, really. And the way it works is we use a magnetic field to polarize the sample to generate our magnetization. We use an RF field to excite the magnetization away from its equilibrium position. We use gradients to spatially encode to move us through K-space. We use an RF coil to detect the emitted signal. And then we acquire the signal in this K-space. Once we've sampled K-space, we use a Fourier transform to generate the image. And there are many different K-space sampling strategies, which I covered a few of, but it's a continuously growing field, and it's a very exciting field to be in. And so I hope that some of you who are new students are going to get a chance to work with MRI and experience just how exciting this field is. So thank you very much for paying attention to the talk, and I'll take any questions that you have.
Thanks, Jamie. Great talk. Anyone have any questions or additional questions that Jamie can help answer? Either, of course, related to the content or anything you'd like to kind of move forward with in terms of your own research. It's a good time to ask. All right.
Next week, I'm going to talk about MR spectroscopy, which is one of the techniques I mentioned at the beginning. So it's a way of using an MR scanner to measure chemical concentrations in the tissue. So that'll be coming up next week.
So maybe you can, if you're feeling comfortable, unmute yourself and give Jamie a round of applause. Thanks, Jamie. Great talk. And hopefully we'll see you all next week for the MRS talk.